everybody. Welcome to, I think, our 11th lecture here in Chemistry 51C. I think we are now live and recording. During this coronavirus situation that is preventing us from all meeting in the same classroom, we've gone to remote instruction. And I've heard a lot about antibody testing in the media recently. How can we get everybody tested to find out who has been exposed to the COVID-19, to the coronavirus, and who is immune potentially to the coronavirus? So I wanted to find out a little bit more about this because I saw a news article that talked about that Germany is now conducting nationwide antibody testing for all of its citizens. And I thought, why can't my country do that? The Germans really seem to have their act together in just deciding, okay, we're going to test everybody. That's a great idea. I looked at the article and it said, well, they're going to examine about 5,000 authorities are going to examine about 5,000 blood samples every 14 days. So it takes 2 weeks, I guess, to do 5,000 blood samples. You know, there's 83 million citizens in Germany. So I did some simple math and it looks to me like at that rate, it would take them 636 years to test everybody in Germany. That can't be right. So I read a little further in the article and they had a revised number. Maybe there's more than one set of authorities doing antibody testing at the same time, but their more optimistic estimate is that they can do 120,000 tests a day. Well, that sounds pretty good. I mean, I assume they work 7 days a week, but still, I go through the math and it looks to me like if they're only doing 120,000 tests a day, it'll take 2 years for them to test every person in the nation. And that's unacceptable. How come we can sequence an entire 9 billion base pair genome in just a couple of days, and yet we can only do about 100,000 tests a day for an entire country? I wanted to find out more about what's behind the antibody testing. Let's go and take a look. There's nothing new about tests for antibodies. These have been around for I don't know how long, but they're all kind of the same. The point of care tests that they manufacture and send to hospitals where people with no experience can run them and people without a lab bench, I presume, can run these tests. They all look like some little plastic cassette with a strip inside, and you add a sample of blood on there and it gets sucked up there. They all look the same. They probably all work the same. So let's take a look at what these point of care antibody testing kits look like. Why does it take so long to test to see whether people have been exposed to the coronavirus? An antibody's a molecule, just like any other molecule. I've just picked at random one test kit to look at the instructions. You don't need to look at the fine print here. I've done my best to try to figure out what's going on at the molecular level, and that's what we care about in a class like this. So here's, as I understand it, here's how these testing kits work. Let's talk about how they make these testing cassettes and then what the actual process of testing looks like. So somebody has taken coronavirus and cloned out the DNA that encodes for the key proteins in coronavirus. So they have taken out the nucleic acids, RNA. They've taken out the nucleic acids that encode for both the nucleocapsid protein inside the virus and these spike proteins on the outside of the virus that are super good at recognizing human cells or mammalian cells. So I'm just going to take those spike proteins as an example. If you take out the genetic material that encodes for these spike proteins and you put that into the E. coli, you never have to look at the virus again. Now E. coli, you can grow up as much as you want. They'll serve as a factory for overexpression of these spike proteins. You're done with the virus. There's nothing dangerous about these bacteria. It's a laboratory strain. So now they can use E. coli as a factory for creating spike proteins. And they mix these spike proteins with gold nanoparticles. And why would they do that? It seems like about 30 years ago, maybe longer, but it became really popular to use gold nanoparticles as these intensely colored dyes. And proteins and all kinds of biological macromolecules, especially if you have thiols on there, will stick to these gold nanoparticles. And so basically bringing along super intense color and very a strong ability to absorb visible light and leave color behind. So you can basically make these little nanoparticles maybe on the same size scale as as a real virus particle, but they're decorated with coronavirus spike proteins. And that's a chemical, they just make this as a chemical reagent so that they can use in these testing kits for this particular brand of cassette strip. So then they put these particles in this well or near this well, and on this test strip, what they have done is they have laid down antibodies. If you take goats and you inject them with human IgM antibodies or IgG antibodies, gamma immunoglobulins or IgM immunoglobulins, the goats will start to produce their own antibodies that bind to human antibodies. If you inject a goat with human IgG antibodies, the goats will start to produce antibodies that bind selectively to IgG antibodies. And so they've done that. You can buy anti-IgM antibodies that bind to human IgM. They've been prepared in goats. They're very inexpensive. Right? You can draw some blood from a goat. It doesn't kill the goat. People donate blood all the time. They do the same to collect anti-IgG antibodies. And they sell these as reagents. So if I wanted to bind to a human IgG, I could go to a supplier and buy some of these goat antibodies that bind to human immunoglobulins. And they have laid these down in lines. This line down here has a goat anti-human IgM. It binds to human IgM antibodies. And this little part of the test strip contains antibodies from a goat that bind to human IgG. So now they've got this test strip in the cassette, and they've got this well. And what they sell you this test strip, and what you in your hospital or in somewhere in your laboratory can take human serum. You could take whole blood, but if you add a clotting agent, the blood cells will fall to the bottom and you're left with this liquid called serum. And that contains all the antibodies, growth factors. That's the liquid part of the blood. So if you put a drop of serum or even whole blood on here, it will contain all the antibodies that are present in your blood. Antibodies for flu, if you got flu last year, antibodies for the common cold, if you had the common cold. It'll contain antibodies for all the things that kind of provide a molecular record of your immunochemistry. So when you take human serum from a patient and you mix it with this reagent, if you have antibodies that bind to the coronavirus protein, it will start to stick to these gold particles. And then you add some buffer here, and that the liquid will start to move across this test strip. It's just drawn by capillary action. We'll just start to move across here. And if you've got IgM antibodies that bind to COVID proteins, to coronavirus proteins, they'll get stuck here and they'll bring along that intensely colored gold, those gold nanoparticles. You'll be able to see those easily because these particles are so intensely colored. Any other IgMs you have that don't bind to coronavirus won't bring along the colored gold particles. So there's other types of IgMs that aren't sticking to gold particles that are here as well. And if you have IgG antibodies that bind to COVID proteins, those will stick to the goat antibodies here in the IgG section. And then they have just a control section just to make sure that the strip is working. That better light up every time. So you have the ability using these test strips, these kits, to tell whether you've been exposed recently. In that case, you have these low affinity but high valency IgM antibodies against COVID, or whether you've had the disease some time ago and have really high affinity antibodies and your immune system is basically got you prepared so you're now immune to COVID, then you'd have IgG antibodies. And this just seems like a really slow process. You put a drop of serum on here, you sit there and you wait 15 minutes for capillary action to bring this through. How are you going to do 1 million of these tests a day if this is the technology? You guys get out of this class and go develop something better that's very high throughput so that when the next disease comes along, we're ready to test millions and millions of patients a day and not 100,000 patients a day. That's not enough for us to be testing entire populations on an ongoing basis for diseases. Monday, we talked about the formation of imines as a way to form carbon-nitrogen double bonds from aldehydes and ketones. And let's go ahead and talk about the mechanism for imine formation. When you take an aldehyde or a ketone and you condense it, that means you release water, you condense it with an amine. And recall that a key requirement for this reaction is that you start with amines that have two H's on the amino group. So R can be alkyl or an aryl group. And those are the cases where you get effective imine formation. The reaction is particularly effective when either the R group on the amine is an aryl ring, like phenyl, or when the aldehyde or ketone is substituted with a phenyl group. Let me go ahead and take an example like that, where we take aniline, that's a phenyl group attached to the amine, and we condense that with a simple aldehyde like acid-aldehyde. And let's go ahead and follow the pathway for that reaction. So the reaction is going to start off with the addition of the amino group to the aldehyde, to the carbonyl group. And you don't need any special assistance like protonation of the carbonyl to get that amino group to add. That would be true if you were trying to get oxygen to add. You'd have to protonate that carbonyl first. We'll see more of that later. And so the next product that you get now has 4 substituents. I'm going to draw the H that was on that aldehyde. Now has 4 substituents on an sp3 carbon. 2 of those substituents are heteroatoms. This is usually a very frustrating situation for an sp3 carbon atom, because one of the heteroatoms really wants to leave in this situation. So the next stage of this reaction involves the acid. Recall that I told you need a weak acid in these reactions, but I told you to be specific about what that weak acid is. It's usually acetic acid. It's not a dilute solution of a strong acid like sulfuric acid. Taking dilute solutions of strong acids doesn't make them weak. A weak acid is an acid that has an intrinsically modest pKa, like acetic acid. And that's the inexpensive acid that we use. Let me go ahead and draw out a symbolic representation of our acid catalyst. We don't need to worry about the exact species that's involved here. We just need to symbolize that with some symbol like HA. So I'll go ahead and show that O- picking up a proton. And, and this is the first role that the acid plays in this reaction. Let me go ahead and draw out that next species here. And here we have our ammonium ion. Anytime you have 4 bonds to nitrogen, you better have a positive charge on there. That's the only type of species we're going to see with 4 bonds to nitrogen. So now, when you deprotonate the acid, you release the conjugate base. I'm going to draw that conjugate base down below the molecule, because then it's very close to this ammonium ion, and we can see how it deprotonates. So let me pull that proton off and give the electrons to the nitrogen. And so now, that's going to generate kind of a semi-key intermediate. It even has a name, where we have all neutral species. So here's the pieces of our aldehyde. There's the H that was on the aldehyde. Here's the oxygen that was on the aldehyde. There's the H that came from our acid. Here's the nitrogen that was part of the nucleophilic amine that added. And we've lost one of the H's that was on that NH2 group originally. We refer to this species as a carbonylamine. I might refer to that later, but it's not a super important intermediate to be worried about the name of that. But if you hear me say carbonylamine, it's this intermediate in imine and in enamine formation that we'll see shortly. And this right here is the tough step. This step right here is why we need acid. We have to turn that OH into a good leaving group instead of a lame leaving group. So hydroxide can leave if you have a super nucleophilic lone pair, like a carbanion or an alkoxide next door. But if you only have an amine lone pair here, we really need to protonate that OH in order to make it leave quickly. And so this is why we add acetic acid to this reaction. 10 times more acetic acid, and this slow step here, this is the slow step in the mechanism, will speed up by a factor of 10. That's just basic law of kinetics here. This is the rate determining step for the reaction. So this process of, it's actually equilibrium, and so you're shifting the equilibrium is another way to view what's happening here. But we've got to get that OH protonated so it can act as a facile leaving group. And so now that we've got a great leaving group here, effectively water, now it's easy for this amine to just push that right out. There we go. And that ensuing, and this is why we call it a condensation, is we release water in the reaction. And so now we've generated our imine. This is the, well, we're almost done generating our imine. We've generated this key species. I'll draw the H that used to be on the aldehyde. We don't have to do that. This species right here is really the important species for this reaction. It's not an imine yet. This is what we refer to as an Iminium Ion. Let me go ahead and label that down below here because it's an important species. It's one of the most important mechanistic species in organic chemistry. It's one of the most important mechanistic species in biochemistry. It's one of the most important mechanistic species, Iminium ion. And you're going to need to know all of these steps when we talk about enamine formation very shortly. I'll reproduce all of these steps as we talk about enamine formation, and I'll remind you of the importance of an Iminium ion. Now, we still have, if you've kept track of all our species, we generated the conjugate base from our acid, A minus, a little while. So let me go ahead and draw out that A minus just to remind ourselves that there's something with a negative charge floating around. And so that conjugate base that's left over can pull the proton off and generate a neutral imine. And even though the Iminium ion is the important mechanistic species, synthetic organic chemists like to isolate neutral compounds. So if we were to isolate a product from this reaction and measure a chemical yield, like for the imine, we would want it to be neutral. And so that's why we keep going. But the real mechanistic excitement here is that we generate an Iminium ion. And Iminium ions are so reactive in every single way. Things want to attack the C double bond N. Water that's generated will come back in and attack and drive the equilibrium backwards. You can deprotonate on the carbon. You can deprotonate on the Iminium ion. Enzymes love to generate Iminium ions and do other things with those. And this is a key intermediate in those browning reactions that I mentioned in our last lecture in the Maillard reaction for the browning of foods. Well, let's go ahead and take a look at another class of compounds that you generate when you condense amines and generate water as a byproduct. That's what condensation is. When you generate amines using, when you react amines with carbonyl compounds like aldehydes and ketones specifically. Let me go ahead and talk about this other process. Ooh, this has a mistake on here. When you condense amine, secondary amines with aldehydes and ketones. Let me be more specific what I mean by secondary amine. This is a weird type of nomenclature. I'll help you understand where that nomenclature comes from. When you have two alkyl groups in one H on an amino group, so ethyl, methyl, phenyl, and methyl, in those cases we call this a secondary amine, a little bit like a secondary carbocation. So when there's only one H on here, you can't generate an imine. For the imine, we had to deprotonate twice. Let's go ahead and take a look at how this reaction works. So if you have an amine that has only one H on there, let's go ahead and draw out what would happen if we took a carbonyl compound and instead of adding a primary amine, we add an amine that only has one H on it. I'll take dimethylamine as an example. And we condense this in the presence of our acid catalyst. The book writes weak acid. I told you, I don't want you to write the word weak acid. That tries to overly mystify what's going on. Just write acetic acid, right? It's not like you don't want to add HCl or sulfuric acid. Those will just protonate the amine and then it's over. Everything's dead. So you add something that's not a strong enough acid to protonate all the amine. And when you add a catalytic amount of acetic acid, these condensation reactions reach equilibrium very quickly. So in these cases, the product of the reaction, there is water as a byproduct, as we talked about before. You're going to generate the carbon-nitrogen bond here, but we can't form a double bond here and generate a neutral product. When you deprotonate from the carbon. That's where the second proton comes from when you get water. Let me just write down, I usually don't ask you to show the byproducts of reactions that don't contain water. When I say show me the product of the reaction, I usually mean the things that contain carbon atoms from our starting materials. So the two H's here on your water byproduct, one of them comes from your amine, the other one has to come from a CH. So that's enamine formation when you do secondary amines. Let's take a look at another common example. People often like to make enamines using cyclic amines, cyclic secondary amines. Here's an amine called pyrrolidine. We're going to have a whole chapter on amines that we'll cover later on in the textbook that we're using. And again, we use a weak acid, acetic acid. Let's be specific about that. And then the product of this reaction, when we generate water as a byproduct, one H will come from the amine, the other one has to come from one of these two carbon atoms on either side of that carbonyl. So I will arbitrarily draw that double bond that we create over here. When you look at this reaction, you know, I think it's obvious that you formed a CC double bond. That's really half of the picture. The important thing is we removed a proton from one of these carbons. That's really the important aspect of this reaction. Now, I mentioned this problem that there's protons on both sides. So how do you decide, how does the mechanistic intermediate decide whether it's going to pull a proton off of the left or off of the right? It can't. You'll get a mixture. And so that's why this reaction works best with symmetrical ketones, where if I pull a proton off the left side, I'll get the same product as if I pull the proton off of the right side. No chemist wants to isolate mixtures of compounds. That's disastrous. Okay, let's go ahead and take a look at the mechanism for enamine formation. You know, that mechanism we drew for iminium ion formation and ultimate conversion to the imine was a 6-step mechanism, and it's virtually the same for enamine formation. This should look very similar to you because we generate the same kind of Iminium Ion Intermediate in these reactions. So if this looks very familiar, then good. So let's go ahead and talk about how you generate Iminium ions and how that ends up forming enamines with secondary amines. So I'm going to go ahead and take as my example. I'm not going to be specific about what two R groups are attached to our amine, right? It could be a cyclic amine, it could be a methyl and an ethyl, two methyls. And in this case, instead of an aldehyde, I'm going to go ahead and draw a ketone. Acetone is a simple ketone. And the reaction starts off with attack on the carbonyl. There we go. You attack the carbonyl. Amines are nucleophilic. They can easily attack a carbonyl. And so the next intermediate we're going to generate now, this would work with aldehydes too, if we had an H on one side and an alkyl group on the other side. So there's that central sp3 carbon in our system, and we've got two R groups attached to this amine. I want to see that H kind of sticking out there for us because we're going to need to pull that off in a little bit, not yet. So we generate this Switter ion. It's got two charged atoms, but they're not directly attached to each other. If the two charged atoms are directly attached to each other, we refer to that as an ylide. But these have a one carbon, two carbon. If they have any carbons or atoms in between, it's not. We call that a Switter ion. So let's go ahead and draw out the role of the acid in this reaction. What's that acetic acid doing? Well, it's creating acidic species in solution. We don't need to worry exactly about what that acidic species is. We symbolize anything that can donate a proton in our reaction mixture as HA, and we don't worry about what that acidic species is. It could be another ammonium ion, could be the acetic acid. Who cares? It's too complex for us to try to keep track of all that, and so that's why we use this symbolic HA. So when I ask you for an arrow pushing mechanism that's acid-catalyzed, use HA and A- as your acid and conjugate base. If I ask you for actual reagents, don't write HA. If I ask you for actual reagents, we don't have bottles of HA sitting around in our laboratories. So then you have to give actual real reagents when I ask you for reagents. Okay, so we've generated this intermediate where we're almost ready to make the water act as a leaving group, but it's not quite ready yet. So here's our ammonium ion that's still there. We need to do a little more work. And if you've been keeping track here, that A- is still floating around. I'm going to draw it underneath for this next step. That way it's a little bit closer. You can see it's just kind of poised next to the, I've drawn it that way, so it's poised next to this ammonium ion because I knew in the mechanism that the A- deprotonates that next. And so now we get to this mechanistic intermediate, again, called a carbonylamine intermediate. Let's go ahead and draw this out. Now everything's neutral, and I'm not going to write the word carbonylamine. I don't feel like that's a super important enough mechanistic intermediate for you to know the name of. And again, we get to this slow step to the reaction. This is the step where that really is why we need to add catalytic acid to this reaction. So when we deprotonate here, we regenerate HA, and this is the tough part, getting a proton on this OH. There's a lone pair down below on this nitrogen that could push out hydroxide, but that's slow. Lone pairs on nitrogen are not as nucleophilic as O- or carbon-. So we really need, if we want fast rates in this reaction, we really need that acetic acid in there to get some protons on these OHs. And so that increases the concentration of species where the OH is protonated, and now is really a fantastic leaving group. And so now, boy, I don't have a lot of room here. Let me see if I can squeeze in these two R groups here. There we go. And I'm going to draw those nitrogen lone pairs. Now that we've turned water into a fantastic leaving group, that is just going to instantly push that out. You've seen water act as leaving groups in SN1 reactions. Compared to a nitrogen lone pair pushing out water, all that SN1 stuff that you learned in earlier parts of the course, totally lame. This water group is going to just shoot right out of there. Okay, now we've generated our key intermediate in this reaction mixture. This is the one that's exciting and is responsible for so much chemistry in biology and synthetic organic chemistry. This is our Iminium Ion Intermediate, right? Let me go ahead and I'll go ahead and write it in black here. But this, once again, is an Iminium ion. It's a CN double bond with an N+. That means it's easy to attack that carbon atom of the Iminium ion. It's easy to deprotonate. Now we have R groups on here. We don't have H's. And so we don't have a choice to generate an imine here when there's only R's. So if we're going to deprotonate somewhere and generate a neutral nitrogen, we need to draw out the H's attached to this carbon atom. And you'll recall way back over here when we deprotonated, we generated A- as a byproduct. So let's go ahead and draw that A- here. I'll just put it right there next to that CH. And so when we deprotonate, we push these electrons all the way over in order to end up with a neutral nitrogen atom. Now I have a choice here. I can make the electrons end on the bond, but I like to make it attack the atom. You can also make it end on the bond. Either way is okay. Just be specific and precise about where you make your arrows end. And then I'll push these electrons up to the nitrogen so it's no longer charged. That'll give the nitrogen a lone pair, and it will now be neutral. And so the product for this reaction, this condensation where we release water as a byproduct, is now an enamine. This is the mechanism for enamine formation. Everything up to the Iminium ion is the same mechanism as for formation of an imine. It's only that last deprotonation step that differs. And I expect you to know both of those mechanisms, backwards and forwards. You can hydrolyze enamines. It involves exactly the same intermediates, and all you change is the arrow pushing when you're going backwards. You draw the same intermediates, but use different arrows. There's a principle called the principle of microscopic reversibility that says any reaction that goes in one direction under a set of conditions, if it's going backwards and is in equilibrium, it has to be going through the same intermediates. Now, imines and enamines are not completely stable, right? Now, let me go ahead and first draw out essentially an equilibrium, and then we can talk about that issue. It's very common to make enamines using cyclic amine. So here would be one cyclic amine called morpholine if I put an H on the bottom. And if you condense that with cyclohexanone, you'll end up generating an enamine that looks like this. That's kind of complex because if I show you this, maybe if you haven't practiced this reaction, you better practice. You might forget that this came from cyclohexanone. There used to be a carbonyl here. But you can hydrolyze that right back. So we can draw this out as an equilibrium process, or we can draw it out as a synthetic transformation. And I'll first kind of draw this to lead us into this idea that it could be thought of as an equilibrium process, where we're paying attention to things like equilibrium constant and things like this. So if I pay attention to the fact that this is an equilibrium process like this, the equilibrium lies very heavily on this side. You need acid, catalytic acid of some kind to make this reaction work. So I'm just going to write catalytic HCl would catalyze this. You could use catalytic acetic acid, but here you don't care if you protonate the amine because you're trying to generate that. Generally, these reactions are very favorable because C oxygen double bonds are more stable than C double bonds. They're way more stable. So much of organic chemistry, biochemistry is driven by the formation of carbonyls, CO double bonds, because they're more stable than CN double bonds or CC double bonds. The downhill reaction in burning fuels is that you generate carbon dioxide as those strong CO pi bonds in there. Now, this is what I would draw if I wanted to emphasize Le Chatelier's principle and the fact that water drives it this way, thermodynamics of the CO pi bond drives it that way. But if I want to think of this as a synthetic transformation, then I would not draw the water as a reactant. I would usually draw that out as a reagent or as a solvent. So if I were trying to emphasize this and I said, supply reagents to affect the following transformation, and I drew these as the products, and you had to supply the conditions and the reagents, then we would typically just draw the water down below to indicate that it's a solvent. You know, when you take common solvent molecules and you draw them below the arrow, the reader assumes that it's being used as a solvent. If you put sodium chloride below the arrow, that's not going to be a solvent. Nobody would assume that's the solvent for the reaction. But things like water, tetrahydrofuran, acetone, those are common solvents. When you draw them below the arrow, you know they're in excess. And here I would just write my reagent, catalytic HCl, above the arrow. If I didn't write catalytic, the actual product of the reaction would be the ammonium chloride salt. The amine would get protonated by the HCl. We're going to have a whole chapter on that later. So in other words, here I'm showing them as reagents. Here I'm emphasizing the equilibrium, and here I'm emphasizing the reagents and transformation. So kind of mechanistic thinking versus synthetic organic chemistry thinking. Let me emphasize a tricky component of these reactions. The mechanism for hydrolyzing enamines is the reverse of the mechanism for formation. It involves the same intermediates. But the first step of these, the mechanistic first step in these reactions involves something that I think is very hard for people to see. For some reason, students who are just learning about enamines have a hard time recognizing step one of the hydrolysis. The mechanism for hydrolysis, if you have some acid in there, I'll draw it symbolically as HA, involves protonation of the carbon, not the nitrogen. And that's really hard to see. We're going to talk more about enols and enamines and enolates, where double bonds are reactive because there's a lone pair next door. And the reaction, the first step of the hydrolysis mechanism, involves protonation of carbon. Right there. Let me go ahead and draw that. I don't draw the arrow starting from the carbon. You always draw the arrow starting from electrons. So that's the first step of the 6-step mechanism to go backwards. And for some reason, that's just very hard to envision when you're just, for the first time, learning about reactive double bonds like enamines. Wow. Okay, we're done with the condensation of amines with carbonyls to make imines and enamines. So now let's go ahead and talk about water acting as a nucleophile to attack carbonyl groups. The first transformation we're going to see is not really synthetically useful in any way, but it gets us to start thinking about addition of oxygen nucleophiles to carbonyl groups. And I'm going to take just a screaming hot reactive aldehyde. When you buy acid-aldehyde, it is really a pain to work with because it is so unbelievably reactive. It has a low boiling point. When this gets exposed to water, acid-aldehyde is more reactive than longer chain aldehydes or aldehydes with any type of conjugation on there. When you expose super reactive carbonyl groups like acid-aldehyde to water, they can form a species called a hydrate. So let me go ahead and draw out that hydrate species. Generally, these have very poor stability. I'll get to that in just a second. And this is a hydrate. So we've added the elements of H and OH across that double bond. You can look at it either way, but here's the H and here's the OH. So we've added H and OH across that double bond. So that's hydration. Condensation is you lose water. And this is an equilibrium process. And it's usually poor. It's not actually perfect for this. It's so easy to isolate these because if you tried to isolate this hydrate, it would simply be in equilibrium. you can try to isolate this and put it in a flask and it would immediately equilibrate with the carbonyl version. Let's take a look at how favorable or unfavorable hydrate formation is. The most reactive aldehyde that we have would be formaldehyde. That would be this, CH2 with a carbonyl. And it is so reactive, you can't actually buy formaldehyde because it condenses the oxygen atom of one formaldehyde attacks another carbonyl carbon of another formaldehyde. You can't isolate it. And it's so reactive, if you put it in water, 99.9% of the formaldehyde molecules exist as the hydrate. It's so unbelievably reactive. Very challenging to work with formaldehyde without having something add to it. So when you buy formaldehyde solutions for preserving tissue samples, it actually exists as the hydrate in solution. Just putting one carbon atom on that aldehyde to make acid-aldehyde as above, right? It's not that favorable anymore. 58% of the acid-aldehydes will exist as the hydrate, but you'll always have 42%. You'll always have this 42 to 58 mixture when the system is at equilibrium, and it will always be in rapid equilibrium, even if you don't intentionally add an acid catalyst. It's so facile to go back and forth. You could never isolate one of these pure when there's water around because it'll exist in equilibrium. Now, if you take a typical ketone like acetone, right? Acetone, that's a common ketone. The equilibrium is poor. There's almost no hydrate in there. The amount of hydrate that's present when you put acetone in water, only 0.2% of the carbonyls exist as the hydrate. So this is not a synthetically useful transformation. You can't synthesize hydrates like acetone hydrate. This will immediately equilibrate to give water and acetone. You can't stop that from happening. So, but the main point here is to get you thinking about addition of oxygen nucleophiles to carbonyls. Don't try to use that as some synthetically useful transformation to make a hydrate from an aldehyde or a ketone. Okay, let's go ahead and take a look at what's going on mechanistically in this hydrate reaction. This is probably a good reason to talk about hydrates. It's kind of the simplest mechanism to talk about for addition of water to carbonyls. Now, you can catalyze, you need a catalyst, you need a mechanistic catalyst to make it possible for oxygen nucleophiles, like neutral oxygen nucleophiles, to add to carbonyls. It is possible for alkoxides to add to carbonyls, but that has no importance in organic chemistry. Adding hydroxide to when you add base to ketones and aldehydes, the dominant chemistry is formation of carbanions called enolates. We have a whole chapter on that. So the book seems to put a lot of attention into what happens when alkoxides attack carbonyls, but there's really no point in discussing that. So I'm never going to ask you about the mechanism for base-promoted addition of hydroxide anion to carbonyls. That just doesn't make any sense to discuss. But acid-catalyzed addition, that makes sense to discuss. So if you put acid-aldehyde in neutral water, there's enough hydronium ion in neutral water to catalyze the reaction. So this first step, you can't just get water. Let me go ahead and dangle that water molecule underneath. You can't get water to attack at sufficiently good rates. It'll collide with the carbonyl over and over and over, and then just bounce right off. It's only when you protonate carbonyls, aldehydes, ketones, esters, amides, only when you protonate them can you get oxygen nucleophiles like water or alcohols to add at sufficient rates. Now that we've protonated that carbonyl, boy, that oxygen hates being positively charged. Oxygen's electronegative, and you don't satisfy that by attacking the oxygen. Geez, do not attack that oxygen atom. That's not the thing that wants the electrons. The oxygen already has 8 electrons. The way to get rid of the positive charge is to attack the carbonyl carbon. That's how you get rid of that positive charge. Please don't attack the O+. I'm not sure if you can see that. That's too low. That's a lone pair. I'm just saying it has 8 electrons. Don't attack that. This is the pattern of reactivity you need to get way, way, way familiar with. Whoops. Oh, I shouldn't have drawn that double bond. My brain is somewhere else right now. So this is the start of the mechanism here for hydrate formation. We formed a new oxygen-carbon bond, and we still have that A- floating around here. There it is. And we want to get rid of this positive charge on that oxonium species, that oxonium group. So we're going to don't attack the O+. Again, that's got 8 electrons. You want to attack something so that we give electrons back to the oxygen. That's how we're going to get rid of that annoying positive charge, the formal positive charge on that. And so that's the mechanism for hydrate formation. There we go. So that's how you generate the hydrate from acetaldehyde, the mechanism. Okay, so you're going to see this over and over and over again. So I'm just going to write a big reminder to you. Remember this pattern. If you want oxygen nucleophiles to add to ketones, to aldehydes, to esters, to amides, we're going to need to run those reactions under acidic conditions, because oxygen lone pairs are just not that nucleophilic. They're nothing like a nitrogen lone pair or a cyanide carbanion lone pair or a carbanion or an alkylithium. You need that assistance to make that happen. So synthetically, we can make species that have 2 carbon atoms attached to an sp3 atom, but it can't be the addition of water. There is a transformation we can do that looks very similar to hydrate formation. And that transformation is formation of acetals. Let me go ahead and take a specific example here. Let me go ahead and draw out, I'll take cyclopentanone just to be different in some way. And instead of forming a hydrate of that, I could never get a good yield of the hydrate. Nothing I could ever do would give me a good yield of H2O addition across that double bond. But if we want, we can add alcohols to give a species that looks kind of like an hydrate. And we call those species acetals. And when it's derived from a ketone, sometimes we call them ketals, but that's not an important distinction. So we'll refer to the product of this transformation as an acetal. Now, we're not adding the elements of water across this cyclopentanone, but we are losing water as a byproduct. So one of the methanols will add here. There we go. The other methanol will add here. So it looks a little bit like a like a hydrate. And the byproduct of this reaction, so we have to run these with an XS. Sometimes I just write the letters X and S there. So in order to drive, it's an equilibrium process. And the byproduct is water. We have to lose H and OH. Here's the O, and the 2 H's come from the methanol. Let me just emphasize that. There's the O you lose, and there's the 2 H's you lose. H and H, there they are. And so we generate this species called an acetal. There we go, I'll just write the word acetal. Now, these reactions are slow. They reach equilibrium slowly. So what do we do to make them reach equilibrium quickly? You add an acid catalyst. And in this case, you don't mess around. You add a strong acid because you want to get as many of these carbonyls protonated as you can under the conditions of the reaction. This is not like imine formation. Imine formation, you add acetic acid, a weak acid, because you don't want to protonate the amine nucleophile. But we don't have to worry about protonating away all the oxygens in our alcohol. So we go right in with a strong acid. And the most common acid that we use synthetically in the laboratory is paratoluene sulfonic acid. I don't know if you've seen this used as an acid catalyst before, because we haven't been doing catalyzing carbonyl additions by oxygen nucleophiles before. Let me go ahead and talk about paratoluene sulfonic acid. You might have talked about this already back when we talked about electrophilic aromatic substitution. If you take toluene on an industrial scale and you treat it with SO3 and sulfuric acid, it is super cheap and inexpensive to make toluene sulfonic acid through electrophilic aromatic. They sell this in train car fulls. It's so inexpensive. And the reason we use this is that this is a strong acid just like sulfuric acid. It's got about the same acid strength as sulfuric acid. But the difference is that sulfuric acid is a strong acid. When we want powerful acids, and a mineral acid is okay, you use sulfuric acid. And the issue here is that sulfuric acid is an inconvenient liquid. If you're in the laboratory just doing a synthesis and you need 5 milligrams of sulfuric acid. There's no easy way to measure this goopy sulfuric acid that's super corrosive because it's a liquid, and that's inconvenient. Whereas para-toluene sulfonic acid is a solid, and that's a convenient form to weigh out on the balance if you just need a few milligrams or need 22.1 milligrams. Anybody can weigh out a nice solid white semi-crystalline powder. And we, sometimes you'll see us drop the P. Nobody uses ortho-toluene sulfonic acid or meta. It's the para one that they make and sell on industrial scale. So oftentimes we just abbreviate this as TSOH. And we always draw that HOH because when we write mechanisms, we want to be able to make and break bonds between the oxygen and the proton. Okay, so that's the conditions for for formation of acetals. Now, if you want good yields of acetals, you know, you could probably make this acetal, the yields wouldn't be great, then you really want to choose an alcohol that makes acetal formation easy. Let's go ahead and talk about what would make it easy to form an acetal. If you wanted a good yield of the acetal, you got to you choose your alcohol carefully. And so let me just take an example of what would make that easy to do. So in order to make your acetal stable, easy to isolate, and high yielding, if you wanted to make an acetal, one of the most common alcohols that we would use, it's got to have some trick that helps drive that to equilibrium. So if I took benzaldehyde and I wanted to form an acetal with this, you have to drive the equilibrium because carbonyl groups are stable. So you'd have to drive the equilibrium by using the alcohol in excess. There we go. And in this case, we'd add catalytic toluene sulfonic acid. I'll just write our abbreviation there instead of drawing out the structure. I'm leaving out the little para P toluene sulfonic acid because it's always para is the one everybody uses. And so in this case, if you use an excess of the methanol, you can drive the equilibrium to help you get a better yield. But it's still, there's an intrinsic favorability to carbonyls. There's an intrinsic tendency for this to hydrolyze back to give the carbonyl. We usually don't write the byproduct of this process, which is water. And so, you know, the methanol absolutely has to be in as vast an excess as possible to drive the equilibrium towards the product. But when you run these reactions, if you wisely choose your alcohol so that the two OHs are attached to the same molecule, you can get much better yields for isolated yields for acetal formation. So let's suppose I wanted to do Grignard chemistry without this reacting. I can make a cyclic acetal with this. This is a common way to protect aldehydes, is you use alcohols where there's two OHs attached to the same molecule with a 2-carbon linker or a 3-carbon linker. This is called ethylene glycol. It is one of the most common alcohols for making acetals. So you still need an acid catalyst here. And this is kind of difficult to see what's going to happen here. Let me go ahead and draw this out. I feel like when people just start organic chemistry, they have a hard time seeing formation of rings. So here, one OH will form one of the oxygen carbon bonds in our acetal, and the other oxygen will form the other, and those will still be linked together, right? You're forming these bonds here. These are the new bonds you're forming. New bond, new bond. You're not breaking or forming the bonds over here. That's like a different chapter. That's like thinking like SN1 and SN2 chemistry. These are the new bonds that you're forming. I'll just write new, and I'll write new. So here's that ethylene glycol piece. And the two H's that used to be here and the oxygen that used to be on there, those end up in your water byproduct. And we have tricks in our laboratory to help distill the water out or suck the water out of the reaction. Okay, so when you make acetals, sometimes we want to protect carbonyls so we can do Grignard, make Grignard reagents without the carbonyl reacting with other Grignard reagents in our reaction mixture. So converting aldehydes or ketones into acetals, which are completely unreactive to the most nucleophilic reagents we have. No nucleophile will ever add to this acetal. No base will ever deprotonate anywhere around here. As long as you don't expose it to acid and water, which easily drives it back, you can do any type of carbanion or nucleophile chemistry on the other parts of the molecule, and that carbonyl will stay hidden as an acetal in there. All right, so this is the beginning of us talking about using protic conditions, acids, to catalyze the addition of oxygen nucleophiles. We didn't need those acids to get Grignard reagents or alkylithiums to add. We didn't need those acids to get amines to add. We didn't need those acids like strong mineral acids to get amines to add. We did use a weak acid for in our imine and enamine forming conditions, but the weak acid was not there to protonate the carbonyl group. The weak acid was to make water a good leading group. So here for oxygen, we're using acid catalyst to protonate the carbonyl, so even a lame oxygen atom can add. Get out of here, go practice a bunch of problems on this. We've got an exam coming up on Monday, and that exam is going to be on sapling, on the online system sapling, because we're teaching remotely now due to the coronavirus. And it's going to cover electrophilic aromatic substitution, chapter 18, the acidity of oxygen molecules like phenols and carboxylic acids, and it's going to cover that whole chapter, chapter 20, on Grignard reagents, alkylithiums, cuprates, practice hydridoaluminate and hydridoborate reagents. Practice the heck out of those reactions. I'm going to ask you a bunch of reactions. Go practice reactions you've never seen before, because I'm going to ask you about reactions you've never seen before. All right, good luck. Then I'll see you guys on Friday.